Hey guys! In this video I'm going to show you several chemical reactions with elemental boron, and I think you've probably never thought that amorphous boron is actually one of the most reactive solid nonmetals, second only to white phosphorus. To obtain reactive boron, I heated boric acid strongly until it fully decomposed into water and boron oxide. When heated, boric acid first decomposes into metaboric acid and then into boron oxide. The resulting boron oxide, which looks like vermicelli, was then carefully ground in a mortar. This gave me a white powder, from which I plan to produce reactive boron. It's logical to assume that there must be some reduction reaction to obtain boron from this oxide. And as a reducing agent, I'm going to use metallic sodium, which I'll add to the boron oxide in a crucible. Before adding the sodium, I cut it into small pieces, so that it would mix better with the boron oxide. Before placing the crucible into the muffle furnace, I'll cover our mixture with an excess of boron oxide. After that, the crucible can be placed into the preheated furnace and heated for about half an hour at 800 degrees Celsius. Once the furnace has cooled down, the crucible can be removed. Let's take a look at what has formed inside. The gray inclusions in this melt are the amorphous boron that we need. Besides boron, the other main product of the reaction here is borax. To extract the boron, we need to treat the melt by heating it in strongly diluted hydrochloric acid. After this treatment, all byproducts will dissolve, leaving behind a precipitate of fine, pure amorphous boron. The resulting precipitate of amorphous boron must then be filtered and treated with a solution of alkali, after which it should be neutralized and, once washed, placed in a desiccator to dry. This grey powder obtained after drying is the small amount of amorphous boron that I managed to extract from all that boron oxide. To test its reactivity, the resulting powder should be added to concentrated nitric acid. If a bright green flash occurs, that means you've successfully produced active amorphous boron. This element will also produce a bright green flash when rubbed with potassium permanganate, or with any other oxidizer, lead dioxide for example. And this is the reaction with lead dioxide. Clearly, freshly prepared amorphous boron behaves extremely actively when exposed to various oxidizers. So now let's try some more exotic oxidizers, such as selenic acid. This is an interesting reaction. Concentrated sulfuric acid and 70% perchloric acid showed no reaction with amorphous boron. By the way, my next video will be about anhydrous perchloric acid, but for now I'll show you the reaction between it and elemental boron. And now, I'm going to add amorphous boron to xenon difluoride. I think you also expect the reaction to occur instantly, so let's check it. Yeah, that's exactly what happens, but it's somehow not very impressive. Even with potassium permanganate and lead dioxide, the reaction looked much more impressive. And in slow motion, this reaction also looks pretty dull. Maybe the reaction with Decaborane will look more impressive, like in this photo from my upcoming book dedicated to chemical reactions. This is a slow-motion video showing the reaction of xenon difluoride with Decaborane, truly the most exotic reaction in inorganic chemistry you've ever seen. If not, then write in the comments which reaction you consider even more exotic. By the way, here are photos of fuming nitric acid reacting with elemental boron. Since I've already shown the reaction of perchloric acid with boron, I thought it would be appropriate to show the reaction between perchloric acid and Decaborane. Many of you probably remember what happened during the reaction of anhydrous nitric acid with Decaborane. So let's add a few drops of anhydrous perchloric acid to Decaborane. I waited several minutes, and there were no signs of a violent reaction, so I decided to ignite the mixture using a gas torch. The explosion was loud, but my table wasn't damaged at all, unlike after many other reactions with perchloric acid, which we'll talk about in the next video, so make sure to subscribe so you don't miss it. Thanks for watching, guys, there is just a little time left before I release the video about anhydrous perchloric acid. By the way, the upcoming video, just like all the others, wouldn't be possible without my amazing patrons, to whom I'm extremely grateful. If you can, consider joining them, it really helps reduce the financial load of making new videos. See you in the next video.